I'd like to welcome everyone and begin by thanking the Storers or the Storer Endowment who is making possible today's lecture and the lecture that Chris Field will give tomorrow entitled The Jasper Ridge Global Change Experiment at 410 and 100 Hunt, somewhat more technical lecture. Chris is a particularly distinguished visitor. He is one of the world's leading climate scientists working on the ecological or environmental science end of climate science. And I could go through his many awards and spend a long time doing that, so I will try and be very brief instead. Say that he received a bachelor's degree from Harvard, a PhD in biology from Stanford in 1981. He's a member of the U.S. National Academy of Sciences and has many other honors. He is the director of the Stanford Woods Institute for the Environment at Stanford, and he has a number of other appointments at Stanford, and previously he was director of the Carnegie Institution for the Carnegie Institution for Sciences Department of Global Ecology. He has played a prominent role on serving as co-chair of Working Group 2 of the Intergovernmental Panel on Climate Change from 2008 to 2015. And we're very fortunate to have Chris here to speak to us today on Climate Change 2017.
Thank you, Alan, and thanks everybody for braving the harsh weather to come to a talk on a Wednesday afternoon. What I'd like to do is speak for a few minutes about where we are in our understanding of the climate challenge. What I really want to focus on is where we are in our understanding of the opportunities for building climate solutions. And I think we've finally turned a corner where solving the climate challenge is more about opportunities than it is about threats. I'm really going to talk briefly about 5 things this afternoon. The first, I want to say just a few words about where we are in the trajectory of warming. Those of you who are climate news nerds have probably noticed that there's another dust up about the warming record, and I want to put that to rest. Our understanding of climate impacts has really changed in the last few years, and especially since the release of the most recent reports from the IPCC. We know much more about where the threats are and the magnitude of the threats from a changing climate and where the opportunities are. The real focus is going to be on the nature of the solutions, new insights about solutions, and new insights about the aspects of the solutions where we don't yet have all the pieces. Talk about 2 key features of the Paris Agreement that aren't often considered and recognize the fundamental importance of working in an environment, the first time ever in the history of the world, where we have a universal binding agreement to address climate change. And then finally, I'll close with a few comments about the dynamics of the current political landscape, and although it creates a number of challenges, how that also may create a couple of opportunities. The first thing, and probably the most important consistent theme in the remarks I want to make today, is that we need to process climate change as a challenge in understanding, managing, and reducing risk. Dealing with a climate challenge isn't about understanding the specifics of what impacts will occur, exactly where, exactly when. It's processing risk in the same way that we process risks of lots of other things, from economic changes to terrorism, and building a smart framework for doing that. In order to do it effectively, it's critical to recognize that risk of climate change impacts really emerges from the overlap of 3 very different kinds of parameters. We tend to think about risk of climate change impacts being related to the physical hazards, and they play a role, but the risk really has equally important components due to vulnerability, or the susceptibility to harm. You can think about it as a lack of preparedness, and to the exposure, the amount of assets that are at risk. And if you look at risks from natural hazards, in general, the magnitude of the physical hazard, the driver of the changing temperature or the changing intensity of the storms, tends not to be the most important controller of damages. It's often on this hazard and vulnerability side. And the reason that's important is that when we talk about solving the climate challenge, when we bring in the components of adaptation, increasing our preparedness, we're really dealing with hazard, with vulnerability and exposure. Mitigation provides the option of decreasing the physical hazards, and that's really important, but it's far from the only thing that we'll do. A second key theme that I want to emphasize in my comments today is that it no longer makes sense to talk about a trade-off between investments in adaptation and investments in mitigation or decreasing the amount of climate change that occurs. It's because we know that we need to increase investments in adaptation now, and we know that unless we mitigate, there's no way that adaptation will address critical elements of the climate challenge. So the only way we can come up with common sense approaches to dealing with climate change is by simultaneously investing in both adaptation and mitigation. We often think about a risk framing as something uncomfortable or different in the climate world, but in many ways risk provides an even stronger connection with everyday life than the prospect of future changes that are outside the norm. A risk framing helps us connect the extremes we already encounter with extremes that will occur in the future. A risk framing helps us focus on the full range of possible outcomes from a changing climate. And perhaps most important, a risk framing connects the climate challenge with other kinds of challenges that we deal with every day, whether that's challenges in deciding whether to buy a vehicle with anti-lock brakes or not, deciding whether to have fire insurance on a home, or deciding how much to invest in minimizing risks of terrorism. All those are risk management activities that, depending on your perspective, you can say we're better or worse at dealing with, but we have a long history of investments in managing and reducing risk. Let me switch to the issue of warming, and I think most people probably saw that 2016 is the warmest year in the instrumental record since we've been keeping careful global temperatures since the late 19th century. It was warmer than 2015, which was the warmest year in the record by the largest amount, and it was warmer than 2014, which was the warmest year up until then. An interesting feature of this trajectory of temperature records is that we're now more than 1°C above pre-industrial, and the indication is that the pace of warming is if anything, accelerating. That moves us out of a dynamic we were in just a few years ago where people were asking whether or not there had been a fundamental change in the nature of climate change and whether this period from 1998 to about 2012 represented some kind of a pause. The issue that's been in the news for the last couple days concerns whether or not the data supporting the absence of a pause are really credible. Here's the trajectory of temperatures for California. You can see California's warmed about the same as the global average. So when we talk about global scale temperature changes, they line up with those in California. The news the last few days has been based on this analysis of the so-called, incorrectly called, warming pause from 1998 to about 2012. And Tom Carl at his group at NOAA published a paper in late 2015, just before the Paris Climate Conference, arguing that there had been some technical flaws in the way that temperature records had been processed that meant that the actual pace of warming during the period from 1998 to 2012 was in fact more rapid than had been interpreted. And this mainly had to do with misinterpretation of the way the ocean buoy temperatures were recorded, such that during this hiatus period with the recalculation, the pace of warming was just about the same as it was during the base period from the middle of the 20th century until 2012. And if you look at a wide range of periods with the circles being the before correction and the squares being after correction, you can see that there's essentially no difference between the warming during the base period and in any other way of framing the successive periods. Once you do the temperature correction, the little dust up in the media was that apparently there had been some glitches in the archiving of some of these data. But the critical thing to know is that there hasn't been any suggestion that there was any problem in the analysis. And in fact, several groups have now repeated this and have shown really conclusively that those corrections provide a more accurate record of the trajectory of temperatures. Balarajaratnam, who was at Stanford, is now at Davis, did a really elegant analysis asking whether there was in any sense a warming hiatus by asking 4 different questions. Was there a slowing in the trend? Was there any indication that the trend from 98 to 2012 was different from previous trends? Was there a stalling, or was there a change in the year-to-year distribution of temperature increases? And Rajaratnam convincingly showed that by all of these standards, there was no hiatus in warming. And it really helps establish not only that climate change is real and important, but that these year-to-year wiggles in the rate of warming can't be overinterpreted. And I think we need to be cautious about the risk of overinterpreting the recent very rapid warming, which certainly had some boost as a result of the very large El Nino in 2015. But the fact of the matter is that there's no question that we're seeing rapid warming, and there's no question that it's almost entirely a consequence of human release of heat-trapping gases. We also have transitioned now out of the period where the idea of impacts from a changing climate is largely about the future. We've seen a wide range of impactful, consequential impacts of climate changes that have already occurred. We've seen impacts that have been documented from the equator to the poles and from the mountains to the coast. Here's a map from the most recent IPCC report that characterizes the kind of impacts we've seen. We've seen impacts on physical systems, things like the timing of stream flow, the rate of retreat of mountain glaciers, on biological systems, especially with things like the timing of biological activity, migrations, flowering, with the northern and southern limits of species ranges, a wide range of biological impacts. And increasingly, we're seeing documented human impacts of climate changes that have already occurred, and these range from impacts on crop production to impacts on worker productivity. Interestingly enough, we also have transitioned out of a period where the climate science community is saying, well, extreme events can never be attributed with any level of confidence to climate change because there's always a random element. And now there's a robust, and one of the most exciting components of climate science is focused on a topic called single event attribution, where based on very careful analysis of the expected probability of extreme events under unaltered climate and the actual climate, we can now come up with relatively precise estimates of the extent to which the climate changes that have already occurred have altered the odds of particular kinds of extremes. And these range from extremes of high temperature, where about 90% of the examples that have been analyzed have a human fingerprint. Changes in heavy precipitation, where about half of the events have clear evidence of a human fingerprint, to some really complicated events like outbreaks of severe storms, wildfires in California. One of the most robust sub-areas in climate science is single event attribution, and we're seeing increasing ability to infer the changes in probability that really sets things up to analyze what kinds of compensation might be offered for particular extremes. Here's an example of some really elegant work in single event attribution. This has to do with the California drought, work from Noah Diffenbaugh's group at Stanford. And what Diffenbaugh and his colleagues recognized is that during the historical period, California had hot years and it had wet years, and the probability of a hot year and a wet year meant that, about 25% of the time you got a hot year and a wet year together, and that led to drought conditions. And the drought conditions, the extent of the drought is shown on this Palmer modified drought index, with the browner color showing drought conditions in the upper left quadrant of the figure there. But if you look recently, what you see is that we no longer have cool years in California. We only have hot years, and when you only have hot years, if you still have dry years about half the time, the probability of having a drought goes up dramatically. So with this really simple analysis, simply saying what happens when you change the relative frequencies of warm and cool years, keep the same probability distribution of wet and dry years, it leads to a dramatic increase in the probability of having a drought, including the kind of severe drought that California experienced from 2011 to 2016. And we're seeing more and more consequences of the drought. And this is a beautiful statewide map from my Carnegie colleague, Greg Asner, showing drought-stressed trees in California. About 60 million trees in this image were severely stressed as a result of the drought. And the flights in 2016 showed that a significant fraction of those have already died. But mostly what we want to know is what's going to happen in the future, and how can we take advantage of the things we know about climate change to make better decisions in dealing with the future. And we want to do it in the context of smart management of risk. And a good way to think about it is that the more climate change that occurs, the more we increase the risk of outcomes that are severe, that are pervasive, and that are irreversible. What I'd like to do is introduce you to just a couple of examples of where the science has changed dramatically, and it sort of cements this sense of the motivation for limiting the amount of climate change that occurs. The first place where the science has really changed in just the last few years is an understanding of the risk of large amounts of sea level rise from very rapid loss of ice sheets, especially in the Antarctic. For a long time, it's been relatively well understood that there was a process called marine ice sheet instability, such that as the receding edge of a grounded ice sheet, one where the ice is sitting on the sea floor but under the sea level with a retrograde slope, downward sloping to the center of the continent, reaches an instability point where once the grounding line moves landward of the highest point on the slope, the ice sheet will decompose in a way that's self-sustaining, independent of whether the temperature cools or not. Rob DeCanto and his colleagues recently came up with another important mechanism that's accelerating ice sheet loss that had previously not been incorporated in the models, and it's called marine ice cliff instability. And what DeCanto and Pollard realized from observations is that when ice cliffs are taller than about 100 meters sticking out of the water, they're not strong enough to sustain themselves, and the cliffs collapse under their own weight. In a similar way to moving the grounding line back toward the center of the continent creates this marine ice sheet instability, it can also create the marine ice cliff instability that works with the marine ice sheet instability to amplify. And the consequence of this amplification is an amount of sea level rise in the simulations that's about twice as much as we had without the marine ice cliff instability. And in the simulations that they show here, in a world of continued high emissions, we get a little more than 1 meter of sea level rise in the 21st century from a world of continued high emissions, almost none from a world of ambitious mitigation. There are going to be a bunch of points here where I contrast the difference, the avoided damages, between ambitious mitigation and continued high emissions. So a meter of sea level rise on top of the thermal expansion and the contributions from Greenland and mountain glaciers is a really, really big deal. That's existential for many island nations and for coastal communities around the world. But the real kicker with large amounts of sea level rise driven by the self-sustaining collapse of the Antarctic ice sheets isn't what happens through 2100. It's what happens in the longer term. And if you look through 2500, what you're seeing is that the world of continued high emissions through the 21st century results in 16 meters of sea level rise on average by 2500, with this commitment being independent of whether the climate challenge is solved after 2100. And that, of course, is existential for coastal communities around the world. That is a truly bright line about whether we're in a world where anything like current approaches to sustainability are viable. Really, really big deal. A big change in our understanding in just the last couple of years. The other topic that I want to talk about in a little bit of detail concerns what we know about economic damages from a changing climate. And this is the figure from the IPCC volume that I coordinated. And there are two takeaways from this. It's that aggregate economic damages, as we understood them in 2014, were really modest as a result of a changing climate. You can see these are numbers that are mostly on the order of a few percent of GDP at warming up to 3C or so above pre-industrial. The other thing that's striking is how old most of these numbers were. Most of these date from the 1990s and the few years after 2000. Marshall Burke and his colleagues, Stanford and UC Berkeley, have recently done a dramatic new analysis based on observations of the macroeconomic performance of countries around the world. And what they see is if you look at parameter after parameter, here's the amount of labor supply, labor performance, crop yield, you tend to see these either plateau and steep drop-off or else hump-shaped responses. And when they built equations to describe those, the equations consistently lead to these hump shapes where rich countries tend to be on the side where warming increases economic performance, and where for poor countries, warming decreases economic performance. If we project this into a map of the world, the pattern is truly dramatic. So bluer colors are increasing per capita GDP, redder colors are decreasing per capita GDP. And in the simulations here for a world of continued high emissions by 2100, you can see that Europe comes out a net beneficial as a consequence of the warming that occurs, increase in per capita GDP. The US is hardly impacted, and many of the world's poor countries have gigantic impacts that are larger than 50% per capita losses in income. Strikingly, the implications of warming with a world of continued high emissions by 2100 leads in this analysis to a global decrease in per capita GDP of over 20%, especially taking advantage of observations that the impacts of climate change tend to hit economic growth as well as current year output. This is a topic that Fran Moore, who's on the faculty here now, has made big contributions to. But there's something about this aggregate economic performance that really doesn't capture the essence of the climate challenge. And I want to spend just a minute talking about the way we process the meaning of impacts. There's a tendency to say, well, can't we come up with some master metric that tells us how serious and consequential the impacts are? And I increasingly think the answer to that question is no. There are a wide range of legitimate different perspectives around the world. And what we need to do is create a climate regime in which stakeholders with those different perspectives can come together and work on the issues, recognizing that there are going to be some incompatibilities that are just fundamental to the nature of the problem. In the IPCC, we came up with 5 different ways to think about the value of the assets that are at risk in a changing climate. And in many ways, the questions are, well, how much do you care about the interests of the wealthy versus the interests of the poor? how much you care about the present versus the future, and how much do you care about the things that are easy to assign monetary values versus the things that are hard to assign monetary values. So when we look at global aggregate economic impacts, the things I was just talking about, those fall into this global aggregate economic impacts. And when you look at the risk from a changing climate, what you see is that that tends to be the area where we're really the safest. When you look at unique and threatened systems, those things that are hard to assign economic value, an archaeological site, a single endangered or threatened species, an island nation with a rich culture but not that many people, that falls into this unique and threatened species systems where we're already seeing measurable impacts and where there's a really profound issue with risk becoming very high with warming in the range of only 2°C or more above pre-industrial. The issue of collapse of ice sheets falls into this large-scale singular events, and it's really important to recognize the existential component of several of the risks in this large-scale singular event. Some of those mean that whole nations disappear. Others mean that processes that release vast amounts of heat-trapping gases from ecosystems, such as thawing permafrost, start working on autopilot. And they're ones where our ability to intervene is either very limited or non-existent once a certain threshold is passed. These are the classic tipping point events. Okay, that's what I want to talk about in terms of where we are in the climate science. And I want to transition to spending the second half of my remarks focusing on climate solutions. And I'd like you to think about the details of some of the things we talked about, because the solutions interact with those in very intimate ways. Think about a solution space for climate, and I love this picture of this floodgate. It's in the port of Rotterdam in the Netherlands, and this is an example of an ambitious engineering approach to climate change adaptation. These big gates can be closed across the waterway and protect the port during times of high water, which increasingly occur. And there are a few places in the world where we have the resources and the technology to provide this kind of protection, but it's hugely expensive and it's not going to be available everywhere. So the important starting point is that climate change is a challenge in managing risks. Second, it's important to know that adaptation is no longer just a hypothetical, that we're really seeing experience with adaptation, like the flood barrier in Rotterdam. We also are seeing more and more experience with mitigation, and we're seeing experience that's driving down the cost and driving up the performance of mitigation activities. And then finally, I'm going to talk quite a lot about an increasing body of evidence that's showing that the previous way we framed the problem, which was fundamentally about a series of trade-offs where you could either invest in adaptation, you could invest in mitigation, or you could invest in economic development, aren't really trade-offs at all. And many of the best opportunities represent win-wins between two of those three, or win-win-wins among all three. I want to say one more thing before I move on about the motivation for thinking about co-investments in adaptation and mitigation. The bottom two panels here, a world of 2100 with ambitious mitigation and with continued high emissions, and you can see the temperature trajectories based on the simulations here. The critical point I want to make is that over the next few decades, even in the world of ambitious mitigation, the one in the blue, the temperature trajectory is broadly overlapping with that in the world of continued high emissions. Where you see the black arrow there's not really a significant difference in the temperature outcomes, even with ambitious mitigation. And this is in many ways an era of climate responsibility, where the changes are baked into the system, we're responsible for dealing with those. The second half of the century is in very many ways an era of climate options, and decisions we make, especially now, have a big influence on the options for staying in the world of ambitious mitigation. And a way to think about what that world looks like is illustrated here, where you can see the amount of warming that's already occurred in the top panel, and compare that with the amount of warming that's projected from now until the end of the century in the world of ambitious mitigation on the left and continued high emissions on the right. And the message is that with ambitious mitigation, we'll see an increment of warming that's about the same as the increment we've already seen. We've already seen lots of impacts, so we'll see lots more. But that's a world that's fundamentally manageable in terms of the kinds of adaptations we can imagine. In this world of continued high emissions, where you can see the most continental areas are more than 4°C, and in most cases more than 5°C warmer than even now, we can talk about projected impacts, but the science on those is incredibly immature. And my characterization of this world of 2100 in a situation of continuing high emissions is that pretty much all bets are off on the nature of the impacts. And when we think about the potential for adaptation to deal with those, adaptation tends to work here. It tends to not work here. I want to say just a few things about the nature of the adaptation challenge. We see a wide range of opportunities to do better with adaptation now, whether it's adaptation to extreme events or adaptation to gradual changes in climate. One of the things that's most interesting about adaptation is that it aligns very well with the kinds of investments that are broadly discussed as relevant to building stronger societies. I think the essence of adaptation is that people are no longer talking about adaptation as a climate solution, but adaptation as a societal solution. So when we talk about adaptation, in many cases the smartest adaptations are investments in infrastructure for communications, transportation, public health, the same kinds of technology that allow developing countries to move goods in and move completed products out are the kind that allow the delivery of emergency services during times of stress. We see lots and lots of examples where the agenda for economic development is exactly the same as the agenda for adaptation to climate challenges. Again, infrastructure for communications and transportation, the strongest ways to enable societies, whether they're technologically advanced or emerging, to really be effective and to realize the opportunities that are presented. A third area where we're really seeing adaptation come into its own is that most of the smartest investments in climate adaptation are equally effective in dealing with non-climate hazards, whether that's hazards from terrorism or hazards from other geotechnical outcomes like earthquakes. Then finally, we're seeing a wide range of cases where investments in adaptation can enhance mitigation at the same time. A good example is improving building efficiency, makes it easier for people to deal with high heat conditions, but it also decreases the amount of energy that's required in buildings. Okay, now I'm going to switch to focus mainly on opportunities for mitigation, for decreasing the amount of climate change that occurs. And before talking about the specific solutions, I want to talk about why we have a problem with climate change. And the reason we have a problem with climate change is that over the last century and a half or so, we as a global community haven't been able to figure out how to allow people to become rich without also increasing their CO2 emissions. And you can see on this plot where emissions go from 100 pounds per person per year to more than 10,000 pounds per person per year, and where GDP goes from $100 a person to more than $50,000 per person on a log-log scale. There's essentially a linear relationship. Independent of country, independent of the foundation of the economy, we haven't known how to make people rich without also increasing the CO2 emissions. And what we need to do is break that relationship so the trajectory of future development is with GDP continuing to increase while emissions decrease. I'm going to focus mostly in the next few minutes on carbon dioxide because of this relationship between per capita carbon dioxide and per capita emissions. But it's important to recognize that that's not the only greenhouse gas, and it's not economic activity that's the only driver of greenhouse gas emissions. Here's the overall greenhouse budget from the recent IPCC report, and a really striking feature is that approximately a quarter of the emissions come from agriculture, forestry, and other land use. Many of these emissions are methane and nitrous oxide. So when we focus on CO2, it doesn't mean that there aren't great opportunities for addressing the problem in other sectors. And in many ways, the ag sector is going to be the most complicated one to deal with because we face increasing global challenges with food security at the same time we need to deal with the climate challenge. The essential feature of the CO2 problem is that it's cumulative. The amount of warming that we'll see in the climate system depends on the cumulative amount of CO2 that's emitted essentially from the beginning of the Industrial Revolution until CO2 emissions reach zero. That has important implications in two ways. One is that if we begin to decrease emissions now, it means we have less of a problem in the future. But it also means, and this is really important, that eventually CO2 emissions have to go to zero. Whether the target for climate change is 1.5, 2, 3, 4, or even 5, eventually CO2 emissions have to go to zero if the warming is going to stop. And the amount of time that is allowed between different targets is really not very big. So if we talk about a world of ambitious mitigation, stabilizing warming at something like 2C above pre-industrial, that means emissions reduction need to start now, and we need to hit zero somewhere in the 2070 to 2080 time period. If we're going to stabilize at 3, we have a few extra decades, but it's not like a totally different world. The cumulative nature of the relationship between CO2 emissions and warming means that CO2 emissions eventually have to go to zero. One example, you can see that we can draw out a budget. If we want to limit warming to 2C, that means the total budget is somewhere between 2,500 and 3,000 billion tons of CO2. We know we've emitted about 2,000 billion tons to the atmosphere, and that means we've got about 800 or 900 left. A terrifying series of numbers comes from how long we've got until the CO2 budget for 2C or 1.5C is exhausted at current emissions rates, and the central numbers are that for a 2C world at current emissions, we've got about 18 years. The more conservative estimate is that we only have 9 years at current emissions until we're committed to 2C of warming. A lot of the reason that 1C is so challenging is that we're already right at the cusp of being at 1.5C, and the central estimate for the amount of time we have until we have exhausted the cumulative budget for 1.5C is 1 year, 7 months, and the conservative estimate is that we have already passed the threshold for commitment to 1.5C. Another reason we need to be serious about the adaptation challenge. I'm not going to talk very much about it, but a critically important component of solving the climate challenge is to make investments in energy efficiency. And my colleague Jim Sweeney at Stanford always emphasizes that the lowest cost, highest impacts investment in solving climate change always occur from investments in efficiency. But we are seeing dramatic progress in a wide range of other technologies that have for the first time allowed us to see a divergence between global scale rates of economic growth and global scale emissions. Some of that is a result of surging success with renewables. A lot of it has to do with the successive replacement of coal with natural gas, especially in the United States. But if you look at the recent trajectory of global scale CO2 emissions, you see a surprising and in many ways encouraging trend. CO2 emissions have in general grown really rapidly from 2000 to about 2013. From 2013 to 2014, which was a year of modest global scale economic growth, about 2.5%. There was essentially no net increase in emissions. 2014 to 2015, another year of modest economic growth at the global scale. No increase, in fact, a small decrease in emissions. And from 2015 to 2016, a third year of decent economic growth at the global scale, a tiny increase in CO2 emissions. This doesn't necessarily mean that emissions have peaked. In fact, they almost certainly have not peaked, and a big reason for the slowdown is slower economic growth in China. But we're beginning to see a divergence in the trajectory of GDP activity and the trajectory of emissions, extremely important. So what are the components we need to talk about? So first, efficiency is almost always the cheapest approach. Good buildings can make a huge difference in adaptation as well as mitigation. Lots of opportunities for changes in industrial processes so that we require less energy to make the buildings, chemicals, and other products that we use. And then there are lots of opportunities for progress with living and working environments so that individuals, all of us, people around the world can aspire to the lifestyles they want that are associated with lower levels of carbon emissions. But then energy technologies are also critical, and much of the most exciting progress has come from recent developments with energy technologies. You know, it's amazing how much wind and solar have improved and how much penetration into the energy system we've seen just in the last few years. From 2006 to 2015, there was a 52 times increase in the penetration of solar, a more than 7-fold increase in the penetration of wind. But the fraction of the energy in the U.S. or around the world that's provided by these renewables is still really, really small and far from taking over as dominant sources of the energy system. That's not because the costs aren't competitive. This is a recent analysis from the National Renewable Energy Lab showing 2014 and 2025 cost ranges for energy production from coal, natural gas combined cycle facilities, solar PV, and wind. And the striking thing is that even though wind and solar have bottom range cost estimates for 2014, a little bit higher than natural gas and coal, by 2025, and based on this analysis, they look like the cheapest alternative. Even this 2015 analysis is looking increasingly out of date, and the changes have just been dramatically rapid. And the technology for wind is advancing amazingly, not only with the very low cost of these super large wind turbines, where this latest Vestas turbine is 7 megawatts per unit. What that means is that 5 of these would provide all the electricity for the Stanford campus. Really impressive. But also an increasing recognition of how to deploy wind in efficient ways. John DeBeery, a Stanford professor, has shown really convincingly how the wake effects from turbines can decrease their efficiency. And he's been a big advocate of these small vertical axis turbines, which have only a few moving parts, can be deployed anywhere and can be deployed at very high density because the wake they create is generated vertically rather than horizontally. We're seeing long-term power purchase contracts for wind that are already cheaper than coal in many parts of the world. And the really impressive recent trajectory of wind is that it's being deployed for economic reasons rather than for environmental reasons. And probably all of you saw, but the 5 states in the U.S. with the highest penetration of wind were all states that the Republicans carried in the 2015 presidential election. And those states have wind not because they're embracing environmental outcomes, but because it's the common sense approach. With solar, we're also seeing some amazing progress. If you look at the recent prices for long-term power purchase agreements for solar, many of those are way cheaper than any other electricity sources. The city of Palo Alto in February of last year signed a long-term power purchase agreement at 3.7 cents per kilowatt hour. There are new facilities that are just going in Chile and in the United Arab Emirates at under 3 cents per kilowatt hour. No fossil energy competes with those. For a long time, people have said, oh, we don't really need to worry about continuing to focus on the energy efficiency of PV panels because we'll just make bigger panels. But we've now reached the point where most of the cost of putting in a PV facility is the cost of things other than the panels. For utility scale solar, installation costs are now on the order of $1.50 a watt, and it's less than 40 cents a watt for the actual panels. What that means is that the next breakthrough in terms of driving down the cost of PV isn't going to be making the panels cheaper, it's going to be making them more efficient, so it takes less of the other stuff to build a balance of system. Mike McGehee at Stanford has recently done some really brilliant work with hybrid panels that combine silicon and perovskite to get the efficiencies up above 25% of total energy in the sunlight converted into electrons. And what that's meant is that we're on a trajectory to drive down the cost of the balance of system in a way that's going to continue to drive down the cost of solar. There's kind of a competition now between Stanford and the UCs about who can get to be carbon neutral most quickly. Stanford just in December unveiled its new 67 megawatt PV facility in Kern County, so it's something for you guys to aspire to. And it also is really clear that we're seeing the sunset of the age of coal, independent of the whatever kind of political backing there is behind coal. And that's for several reasons. In 2016, for the first year, we saw more U.S. electricity from natural gas than from coal, mainly because gas is cheaper. Way more jobs in wind or other renewables than in coal. We've now reached a point, around 50,000 people a year in the U.S. die as a consequence of inhalation of PM 2.5 from electricity generation. A staggering statistic, and there are about 30,000 coal miners. So there are now more people in the U.S. who die on an annual basis as a result of particulate inhalation from coal-generated electricity than there are coal miners. Staggering. Can we build a world of 100% renewables? It's been the big challenge. It's been the holy grail in many ways. And we know a lot of great work here at Davis has focused on the challenges associated with difficult to decarbonize sectors. And there are things we might be able to do. Biofuels provide one way to continue to provide high energy density liquids. Negative emissions of using biomass or removing CO2 from the air provides a way to allow some fossil to continue to be in the system. Or we may find ways to make chemicals from electricity, hydrogen especially. But there are lots of other things that we can do, and I want to spend 1 minute talking about those. Many of the opportunities for doing a better job of meeting the challenge of 100% reliability have to do with not necessarily storing electrons, but finding a better way to get them to where they need to go. And that can come through better integration of the grid, a better management of the devices that are requiring energy, some kinds of storage, and then some kinds of dispatchable power either from nuclear or from fossil with carbon capture need to be in the system. But what can we do with storage? We tend to think about storage as batteries. The problem with batteries is that they're really expensive, and the cost of even these super slick Tesla Powerwalls are still more than $300 per kilowatt hour. Stanford recently just launched a really impressive campus-wide energy management system that's essentially a giant energy storage facility. And in essence, it's 3 giant tanks. 2 of them hold cold water and 1 of them holds hot water. They collectively store about a week's worth of building, heating, and cooling for the university, providing energy storage at well under $100 per kilowatt hour, beating the power pack by at least a factor of 3. However, we still need to do better, and my favorite technology, the one that I want to leave a seed with for you to watch or to conduct research on, is electrolysis. And I'm sure everybody did an experiment in junior high school where you used a battery to convert water into oxygen and hydrogen. As we end up with more and more electricity than we can use in real time, electrolysis provides a linking point to connect electrical energy to chemical energy. And hydrogen can be stored, it can be converted into other chemicals, and it in essence will, if we can make it work, be the holy grail for providing energy storage. And I want to close with just a couple more comments on the practicality of building a 100% renewable grid. My colleague Mark Jacobson at Stanford has been a strong advocate of using ambitious commitments to energy storage to build a 100% renewable grid and ask if we can achieve 100% reliability without having to have fossil or nuclear in the system. And he points out that the intermittency and the potential to generate solar or wind energy is a big problem, but that there are lots of ways that we can modulate the load in order to take advantage of the intermittency. And by very aggressive management of the dispatchable resources, especially hydro, a couple of kind of heroic assumptions about the rate at which entities might adopt things like the district heating and cooling that Stanford's already done. Jacobson comes up with a scenario in which 100% of the grid reliability issues can be addressed with no nuclear or fossil 100% of the time. And you can see the match between supply and demand in the top panel there. There are some heroic assumptions, but previous to a couple of years ago, the general sense in the energy community was that we don't really know how to build a 100% reliable, renewable-based grid. I'm not sure everybody would say we know now, but there are more and more glimmers of a solution with the components that I've talked about, making it feasible to get to much higher penetration of renewables, or really drive us along the trajectory to 100% renewable energy system and zero CO2 emissions. Let me close with just a couple of comments on the Paris Agreement. You know, there have been lots of comments about whether the Paris Agreement was too ambitious or whether it let countries come forward with too much of their own thoughts. And at least for me, there are two key things that came from the Paris Agreement, and they're the foundation for what we need to solve the climate challenge. The first, and I think the most important thing that came from the Paris Agreement, is a sense of what's fair. For decades, forever, international dynamics have been associated with a question of what's fair and what's not on the international scene. And even though individual countries and individual presidents might argue that the agreement isn't fair, every country in the world agreed that the criteria laid out in the Paris Agreement provide a fair approach to solving the climate problem. The second thing that the Paris Agreement does is it establishes a paradigm for what's predictable. And if you ask any company, any country, any community around the world what they need in order to invest in a climate solution, it's knowledge that the policy directions aren't going to change tomorrow. So what's predictable in the landscape is established by the Paris Agreement, as long as we don't pull out. And that's really the thought I want to leave you with, is that the pieces are in place for solving the climate problem, and the pieces are in place for having those solutions build the infrastructure, build the jobs, build the economy of the United States and the world. We just have to stick with it. And we have to stick with it, accelerating the pace rather than slowing it down. Thanks so much. I'd be happy to take any questions. And it's the idea that if you want to ask a question, you should wait for a microphone.
Right, just to hold your hand up and we'll both come around and try to find you. Oh, Alan.
So you hinted at this. One of the issues is how you weigh the future against the present. And standard economic analyses seem to get us into trouble in terms of doing that. Do you have any comments on?
Well, when the United States calculates a social cost of carbon, they use a discount rate, and I don't know, who's an economist here? I'm probably going to get my, Fran. Okay, just ignore what I say. There's sort of two schools of economists. Some people think that you can read the discount rate out of the economic performance, and that it's from observations, and that people always discount the future because you don't know what's going to happen, and there's having a dollar now has benefits over having in the future. Other economists believe that discount rates get built into societies as a consequence of policies that governments put in place, and that discount rates really should be determined based on a serious deliberation by the citizens. The arguments about what the discount rate should be range from it should be really high, who knows what's going to happen tomorrow, to that it should be zero or negative, because there's nothing that's more important, no greater responsibility that we have as a species than to leave a sustainable world to the future. I actually think that the economists have distorted the conversation by putting too much emphasis on the idea that you read the discount rate out of people's behavior, and too little emphasis on the fact that we need as a society to be having a serious discussion about what the discount rate should be. What should the discount rate?
I was just wondering, geoengineering didn't appear on your kind of list of solutions, and I was wondering what your take on that is.
Well, geoengineering, large-scale tweaking the Earth's system in order to slow the rate of climate change, includes two very different kinds of technologies. Carbon dioxide removal, which is really just a different set of mitigation options, and solar radiation management, which is essentially reflecting some of the incoming sunlight away to mask global warming, essentially take another human tweak of the Earth system to try and fix up at least part of the tweak that we can't manage. There is a tiny literature, so I won't talk about carbon dioxide removal. It definitely needs to be part of the portfolio of options that get deployed. Solar radiation management is interesting, but we know almost nothing about it. If you look at the number of papers that have been published on climate change, it's in the many tens of thousands. And if you look at the number of papers that have been published on solar radiation management, it's in the many tens. And so it's critical that we know more about the issues associated with solar radiation management, and especially the social and political requirements for having a manageable, governable system. So I'm eager to see that literature emerge, and until it does emerge, and we need to invest in making it emerge, I don't think it's appropriate to draw conclusions or to count on the possibility of using it. My personal expectation is we learn more and more, it's going to look less and less attractive, and that if it finds its way into the climate solution conversation, it's likely to be at the margins rather than as a mainstream strategy. I think it's one at the back.
So yeah, I was really impressed by your analysis of the disparities. It's been talked about a lot in the press, the disparities between rich and poor countries in terms of the impacts of climate change. And I was wondering in that analysis whether you took into account second-order effects, what the friction between the impacts on rich countries and poor countries will lead to greater impacts for both because of all the stresses we know, geopolitical turmoil. Is that a term in that analysis?
So no, it's a really good point. We know very little about what you might think of as social and economic teleconnections, where a climate impact in Sudan results in social unrest in France. So the way this analysis was done is this was just reading from observations. When there's a hot year, what happens to economic production in the Sudan, economic growth in the Sudan? When there's a hot year in France, what happens to economic growth? And one of the things we're just beginning to understand is one of the most important areas for future research is the nature of the social and economic and cultural teleconnections. And we know a lot about the physical and meteorological teleconnections. My sense is that those in the long run are going to be less important by a lot than these social and economic ones.
A lot of your solutions related to decoupling GDP and temperature, or CO2 production, for example, seem to be related to a sort of a technological efficiency change. But there's a total amount of energy requirement to meet an expectation, which seems almost a sacred cow of the discussion, and it's part of the first point there is what is fair. And it seems about as tractable to address our total consumption, which has an output of CO2 that may change, and the technological efficiency challenges. And so why not address that, the total consumption issue, and treat it as a social engineering versus technological engineering problem?
I love that approach, and I admire the optimism that underlies it. A lot of the reason that I emphasize the technical opportunities for driving CO2 emissions to zero is that if we're going to avoid the worst impacts of climate change, the changes that need to occur over the next few decades. We really need to put in place a zero-emitting energy system by about 2050. A snap of the fingers in the sweep of human experience. And I would love to see serious ongoing conversation about how consumption can be a part of that dynamic. But when I look around the world, there are so many places where there are legitimate aspirations for more secure lifestyles that it's hard to see that we're not going to have to deal to a very large extent with the technical and efficiency components of energy generation. At the same time, I really hope the conversation about consumption and the relationship between consumption and human satisfaction goes on. The essential critical nature of the rapid progress is really important, and I hope that well, let me say one other thing about consumption. When I look at the challenges that result from consumption, they impact almost every aspect of the human experience and the sustainability of the global system. The climate challenge is by far not the one that's most sensitive to patterns of consumption, and I worry much more about the impacts of consumption on biological diversity and on the sustainability of oceans and on not burying ourselves in trash. And I think that conversation needs to go on at about the same pace, and I hope it goes on in parallel to these technological discussions.
Aside from fossil fuels, deforestation is a major contributor of CO2. But you mentioned deforestation very little in your talk, and I'm wondering, is that because you see it as a given that we can't do anything about it, and it's going to either increase or stay the same? Or is there some misunderstanding that I have about how important deforestation is?
Well, until about 1950, deforestation had been the dominant contributor to the release of CO2 to the atmosphere. And as recently as 2000, it accounted for about 20% of annual emissions. As a result of really ambitious actions, especially by Brazil over the last couple decades, it's dropped to only about 10% in the last 20 years, so that even though there's a tremendous opportunity for decreasing emissions, it's kind of at the margin. And when we talk about finding ways to decrease CO2 to zero, we really need to tackle those energy emissions, the 85% of CO2 emissions that come from energy. One of the things that I didn't talk about that my research group is working on now is the idea of creating a future energy system that allows some fossil emissions to continue At the same time, there are negative emissions from some other sectors, particularly regrowing forests. And in many ways, the great opportunity from forests is to go from a net removal of forests to a net increase in the area and the size of forests, something that we've already seen in the United States, in much of Europe, and in a number of developing countries. Vietnam and Chile, for example, have recently undergone a forest transition so that their forests are increasing rather than decreasing.
Can I just add something really quick, Chris? I'm curious if you could also mention the 25% of the carbon dioxide that's taken up by the terrestrial biosphere and how that can factor into these long-term guesses in terms of how much time we have to reduce emissions before an impact is something at a dangerous level, because it seems like that's a high-risk quantity, and I don't know the extent to which it's actually being factored in, so if you could.
Yeah, well, Ben makes the really important point that over the last century we've gotten as human beings a tremendous kind of free subsidy from nature. On an annual basis, about half the CO2 we emit from fossil fuel combustion and from deforestation stays in the atmosphere, and the other half is taken up more or less in equal quantities in the ocean and in ecosystems and land. And when I talked about large-scale singular events, I mentioned that one of the risks is we cross some kind of a tipping point where large pools of carbon on the land, in forests, frozen in soils, are released back to the atmosphere. And when we do these carbon budgets, there are latest generation land models in the calculations, and the expectation across those models is that the land sink decreases through the 21st century, but in relatively few of those is it converting to a source. But if you look across the simulations, one of the most compelling outcomes is that the big sinks of carbon on land, whether they're in forests or soils or in permafrost, are relatively safe in a world of ambitious mitigation, but they're highly vulnerable in a world of continued high emissions.
Okay. I was very taken by the graph of the inequities in terms of the impacts of climate change in different countries too. And I was wondering, is mitigation or adaptation included in some of those estimates? I mean, was Rotterdam closing the gates one of the reasons that some of the wealthy countries weren't as impacted?
So this study was really just based on observations. They said, okay, we've seen ups and downs of temperature and ups and downs of economic growth in every country in the world, and when it was cooler, was per capita GDP and the growth higher or lower? And so the answer to your question is yes, to the extent that people were doing things that adapted. It's in the data, but it doesn't have any kind of ambitious conceptualization of what future adaptation might look like. And the poor countries think that we could obviously be spending more at the global scale to help them adjust to the climate challenge. And a lot of the details of the Paris Agreement are exactly about that, what kind of transfers should occur in order to create a credible sense of fairness out of this pattern of abject inequality in where the impacts occur. I think I need to quit now, is that right?
Yeah, unless there's one.
Wonderful.
Yeah.
Okay,
There's
well.
one.
Yeah, I'm wondering what the potential exploding African population, how that might interact with this.
Yeah, so, the role of human population growth in the climate challenge is really a central one. It's as important as consumption in terms of where we head. The challenge, of course, is that if you look at the trajectory of population growth historically, what you see is that economic growth and improving education, especially of women, are the most powerful ways to bring growth rates down. And so if we want to address the climate challenge and the component due to population, continuing economic growth is certainly a part of that. There have been a few studies, and my group just started working on this, that have said, well, how effective expenditure in climate abatement can you get by meeting unmet needs for family planning? And there's a British group that has argued that by far the cheapest climate abatements available anywhere are investments in family planning for Africa. And the work is kind of preliminary, but I like the approach they've taken, and I think that there are ways to nail down those numbers. And as they get more and more nailed down, I think the role of supporting unmet needs for family planning in addressing the climate challenge will come into sharper and sharper focus. Thanks so much. Wonderful set of questions.